Good morning,
Hello,
Serena.
bom
How are
dia.
you?
I'm fine. I'm tired. So good morning. We start the second week of the school, and this first lecture will be about determinantal singularities. I'm sorry, this week we have the second part of the course on determinantal singularities. So it's the second week of the course number 1, in which we will learn about determinantal singularities, okay? So my first lecture will be about basic properties of determinantal singularities. But I remember that last week, the subject of the last week course was ICES, and I recall that complex analytic space is an ICES if it's defined by an ideal Y is generated by P generators, where P is the codimension. P is the codimension of the ideal. I mean, this much says that X is a complete intersection. And if I say also that the singular set of X is isolated in a small neighborhood of 0, then we have an ICES, right? We saw during the course, well, let me recall this. This is important, that if it's generated by F1 of P like this, F1 of P is a regular sequence, and X has the expected dimension, which is in this case is N minus P, right? Well, we made the connection between ICES, a correspondence between ICES and k-finitely mapped germs, F from Cn to Cp, defined by F1, F2, Fp. And of course, X is the zero set of these germs. And we saw that we can use tools of singularity theory to study the ICES, right? We also saw that an ICES has a Milnor fibration. Well, this is not maybe a good notation, but the ICES is a Milnor fibration, and the fiber is a smooth manifold and has the homotopy type of a bouquet of spheres. And the number of spheres of the bouquet is the Milnor number of the ICES that we denote by mu of X. Finally, we also study equisingularity of families of ICES, and we saw that the infinitesimal machinery we developed can be used to give conditions for the equisingularity of families. In special, we saw that the integral closure of the Jacobian model gives a condition for W regularity, okay? So we want to go beyond our ICES now. So, and determinantal singularities do generalize ices in various aspects. So we want to explain in which aspects determinantal singularities generalize ices, and we also want to understand new properties of this class of varieties. Well, roughly speaking, a determinantal variety is defined by the minors of a given size of a given matrix, right? With the condition that it has this expected dimension. So we can ask why to study them. So there are many reasons, right? So but in algebraic geometry and commutative algebra, we know that there are many classical projective varieties that have a determinantal structure. For instance, Serre, Veronese variety, or normal scrolls, and they have determinantal structure. Frequently, the singular sets and discriminants of smooth mappings are also determinantal varieties. And if we want to proceed with the classification of complex space, we very soon find very simple singularities that have determinantal structure. We saw already this one here many times, right? This is the triple point, is the intersection at the point of three smooth branches. And we know, sorry by the ponto triplo here in Portuguese. So this is given by the 2 by 2 minors of this 2 by 3 matrix, okay? So this ideal that defines this singularity is generated then by these 3 elements, right? Which then repeating is the 2 by 2 minors of this matrix. And I remark that the generators of this ideal do not form a regular sequence, right? They do not form a regular sequence as the dimension of X is 1, right? And we saw already in Terry's lecture that if we take any perturbation of this ideal, we are not always in a good shape. For instance, if you take a linear deformation, this is not a flat deformation because we can get a complete intersection, right? So we can, a small deformation of this ideal can give me a zero-dimensional complete intersection, okay? If you have a question, ask me, okay? Okay. So we have to quickly review the basic algebraic material. In part, they were given by Bruna in her lecture, right? So if R is a commutative ring with unity, I want to define dimension, crude dimension of the ring, and I want to define Cohen-Macaulay models, just this. So, but before I will define determinantal ideals. So let R be a commutative ring with unity. And if we will write R M cross N for the space of M by N matrices with entries in R. And we can sometimes work in other space. For instance, we denote by R M cross M sim, the set of symmetric matrices. And R M cross M SK, the set of skew-symmetric matrix with entries in the ring R, okay? So the definition of determinantal ideal is, as you can expect. So let A be an M by N matrix with entries in R. And so IT, an ideal in R, generated by T minus of A. We say that IT is the determinantal ideal of type M and T. Or I can also say that it's determinantal of type T with respect to the matrix A. Well, we can see right away that the same ideal can be determinantal for different matrices, of course. For instance, the principal ideal I in this space of convergent power series defined by F xz minus yw, you can say it's determinantal ideal of type 1, but it can also be given as a determinantal ideal of type 2, defined by this matrix A here, and so is given as the 2 by 2 minor of this matrix A. Okay? Yes?
In your definition of determinantal ideal, you do not have the expected covalence.
Well, yeah, it's a good point. Yeah, it's a good point. Maybe you're right. Maybe I should put this, because I will define the determinantal variety. I will, for determinantal varieties, I will say that they have the expected codimension, right?
Okay.
And so the basic material from commutative algebra, as I say, just the definition of the crude dimension and the Cohen-Macaulay modulus. So the height of a prime ideal P is the maximum of the length of a chain of strict inclusions of prime ideal, right? P0, P1, Pn. And the crude dimension, or dimension, we also say of the ring that we denote by dimension R, is the maximum of the heights of prime ideals in the ring. For instance, it's not too hard to show the dimension of ON is n, because the case n equals 1 is easy. We have just 2 prime ideals in O1, right? The 0 in the maximal ideal. And then for the higher n, we have this chain of prime ideals. And we can see that we cannot have any other different prime ideal between 2 consecutive prime ideals in this sequence, because the quotient between 2 consecutives is just O1, right? So now I can define Cohen-Macaulay models. We have a local ring, Rm, and M on R model. First, recall that a sequence A1, A2, AR of elements in the ring, in the maximal idea of the ring, is a regular sequence of the model. If A1 is not a zero divisor of M, and AI is not a zero divisor of the quotient M over A1, AI minus 1M for I varying from 1 to R. So I'm going quickly here because, in fact, we saw this in Bruna's lecture last week, right? We defined the depth of M as the maximal height of a regular sequence in M. And it's known that, in general, the depth of M is less than or equal to the crude dimension. And when they are equal, we say that the model is M is Cohen-Macaulay, right? And I can extend the definition to a ring, saying that the ring is Cohen-Macaulay if it is Cohen-Macaulay as an R model, okay? Cohen-Macaulay, so ICEs are Cohen-Macaulay, right? Because they are generated by a regular sequence. Determinantal singularities are not generated by a regular sequence in general, but they have this nice property of Cohen-Macaulayness that will guarantee for us that the multiplicities of the involved algebras are preserved under the formation, right? And this will be a fundamental property in studying invariants and the topology associated to determinantal singularities, okay? So this is the main criterion we need to prove that the local ring of a variety is Cohen-Macaulay. You can find in Egon Rochester a reference that is at the end. So if we have R, a Noetherian ring of dimension D, and if A is a P cross Q matrix with entries in the ring, and IR is the ideal generated by the R plus R minus of A, Then we have that the dimension of the local ring R quotient IR is greater than or equal D minus P minus R plus 1, that's number. And when R is Cohen-Macaulay and the two dimensions are equal, then the quotient ring, the local ring is Cohen-Macaulay. Okay? Any question? Okay. So in analogy with the case of complete intersection, we will say that this P minus R plus 1, Q minus R plus 1, is the expected codimension of the determinantal ideal. And this is the expected codimension of the variety also defined by the determinantal ideal. Okay, so far? We can also, we can change the ambient spacing. Instead of looking at all matrices with entries in R, we can look at all matrices with all symmetric M by M matrices, or all antisymmetric M by M matrices. And we can also estimate the expected codimension, okay? So now we will consider our ring, favorite ring, which is ON, right? Is the local ring of, cadê meu pontinho aqui? Which is the local ring of germs of holomorphic functions at 0 in Cn. So then I will define what is a determinantal variety in Cn, right? A germ of complex space in Cn at the origin is a determinantal variety of type M and T if there is a matrix M by N in such a way, with entries in ON, of course, in such a way that the local ring of X is the quotient ON over IT, where IT is the ideal generated by the T by T minus of A, with the condition that X has the expected codimension, right? So determinantal variety is defined by a determinantal ring with the condition that the codimension is the expected one. So that's okay, my definition was okay. I think we can, in some tests in commutative algebra, they give usually a more general definition, right? So they don't put the condition of the codimension being this one as one of the conditions of the definition. So they take a more general definition, and they do use the condition when it's necessary, right? But for us, that we are looking at the geometric aspects of the singularities, this is a very important condition. Okay, so again, the example that I like to give in the beginning, so that we understand that the problem of studying determinantal varieties and deformations of determinantal varieties is a difficult one. So let's look at this example. It was given by Pinkhams in 1974. So it's a surface in C5, defined by this ideal, which can be given as the 2 by 2 minors of this 2 by 4 matrix, or else by the 3 by 3 minors, or else by the 2 by 2 minors of this symmetric 3 by 3 matrix, okay? So, and we can check easily that it has the expected codimension, of course, but it's known, and maybe we can perhaps even in some exercise occasion to try to do the calculation, that if we deform this matrix or if we deform that matrix, we can obtain non-equivalent, we can obtain deformations which are not topologically equivalent. Okay? So in fact, when we try, if you remember of the construction of versal unfolding that we did in the last week, of course, here we have to do a different construction, but in this case, this versal unfolding of the whole variety, certainly we will have at least two distinct components, okay, with distinct topological types. So, but we can avoid that, and we will avoid that. So then at this point, I would like to explain the viewpoint of the course, right? Any question? Yes.
Topological deformations are worked out in a paper with Rangachev in the archive.
Okay, so Terry and Rangachev worked the details of this example in their paper, okay? So what is our point of view? Our viewpoint is a geometric viewpoint, and we choose from the beginning a given representation. So in the previous example, I could choose to represent that surface in C5 by a 2x4 matrix, right? And I keep with that representation. And in this sense, the deformations that we consider as allowable deformations are the deformations given by that representation, okay? So following Terry Gaffney, we say that the chosen representation gives the landscape of the singularity. So we choose one landscape, and we will understand the singularity from the viewpoint of that landscape. Right? But we can interpret our viewpoint in a much more general way. So in a much more general context, we want to understand the terminal singularities as objects defined as sections of some universal model singularities, right? This more general context will be explained by Jim Damon in his lectures. So let me tell a little bit about this. But in my lecture, in our lectures, in the first lectures, we'll keep this only the case of determinant of singularities. But in general, so what we would like to is then, if we have some universal singularities here, that in general they have singularities non-isolated, right? And frequently these singular objects, they have stratification that are invariant by the action of some Lie group, and they are universal in some sense, and they are stable in some sense, in the sense that they don't change by core elements of this Lie group, for instance, right? So, and then, as I said, this can be very general. This can include determinant of singularities, but also discriminant of stable maps and other more general contexts. So, and then what I want, given this universal object, I want to define and understand determinant of singularities as pullback by F of this universal objects, right? So I want V0 here being the pullback of this universal singularities, okay? So, and in general, we will assume some transversality assumption on F. Okay? So this is important, and we follow then with this viewpoint. In our case, the universal model varieties will be the generic determinantal varieties that I introduced now. So these generic determinantal varieties, they live in the space of matrices, and I give the definition. So I recall that CMN is the space of m by n matrices with complex centries. And I define it there, the variety MMNT as the set of all matrices with rank less than T. If we have rank less than T, that means that all T by T minors are 0. And then this variety is just the vanishing locus of a T by T minors. Okay? We call them generic determinantal varieties. Sometimes I use this, when I use the convention, I use that the minimum between M and N is N. So these varieties, you see, they give a filtration in the space of matrices, right? In the sense that I can understand better now, looking at basic properties of MNT. So first of all, they are irreducible algebraic varieties. It's clear that they are algebraic varieties because they are defined by the minors of a matrix, and they are reducible in the sense that the ideal defining them is a prime ideal. They have the expected codimension. In a way, more precisely, they have this codimension, and that's the reason why the expected codimension will be this one, right? They can be highly singular, and the singular set of M and T is MNT minus 1. And in this way, we can see that we can decompose, we can write MNT as a union from I varying from 1 to T of MNI minus MNI minus 1. So since the singular set of MNT is MNT minus 1, then this set is a smooth manifold. And this is exactly what? The set of matrices of rank exactly I minus 1. Okay? And this union, so it's a disjoint union, is a witness stratification. And finally, MNT is Cohen-Macaulay. So I explain a little bit this. This is just a comment. Before I continue, I just want to say that these are so classical mathematics, right? But from the viewpoint that we are bringing here, in a way that we define the determinant of singularities as pullback of these universal objects, then it's very important to have as much information as I can about these universal models, okay? And this is happening a lot, right? I'm sure that Matthias and even Jean Damon and Terry Gaffney will talk more about this. But I just comment that there's this result by with Gaffney and Grulha, in which we computed the Euler obstruction of this variety recently, I think in 2019. So this is important for the context we are bringing here. Okay. If we assume for a while that we know that this MNR complement of MNR minus 1 in MNR is smooth manifold, then, no, it's better to say in another way. So it's easy to see that, in fact, we have the action of, for instance, this Lie group in the space of matrices, and that this action leaves invariant the varieties M and T and the strata of the stratification. Okay? So, and in fact, the action is the one that we know, right? The action is this one, multiplying to the left and to the right by the invertible matrix. And every time I have a Lie group action in a space in such a way that this space has a stratification in which the strata are invariant by that action, that stratification is a Whitney stratification. So we get this. In fact, it's even more. We will see a little bit more in the next lecture that this stratification is locally analytically trivial. Right? So to prove that the strata which are the matrix of rank exactly R minus 1, that these are smooth manifold, there are several possibilities, right? One of them, which is very elementary, is suggesting this exercise that I leave to you to think, okay? So let's go back to the property. So then they are irreducible algebraic varieties. They have this codimension in space of matrices. The singular set is MNT minus 1. They admit this decomposition, which is a Whitney stratification, and we can show they are Cohen-Macaulay applying the theorem I gave before, right? Okay, so now that we know a bit about our model singularities, I go back to the way we want to look at determinantal singularities, right? So, so if we choose a representation matrix, then this representation matrix gives me a map that I take here, define some open set in Cn, taking values in the space of matrices. Okay, so far? So we have this map whose coordinates are Fij, which are complex analytic functions on U. And I define a pre-image of a model variety MNT here, X as F inverse of MNT. We say that this is a determinantal variety of type MNT on U. If we have that the codimension of X in Cn is the codimension of this model variety in the space of matrix. So it has expected codimension. Okay? So note that when I say that the codimension of the pullback has that codimension, in the complex case, this is equivalent to say that F is generically transverse to the variety. But if we want a condition a little bit stronger, then we come to the definition of EIDS that I will give now. So the EIDS were defined by Ebel and Guzenzad in 2009. And the definition is the following. So suppose I have F from Cn0 to Cm cross n, and the X is the determinantal variety of type M and T. So we say that X has an essentially isolated singularity at 0 if for any sufficiently small representative of F, I have that my map F is transverse to all strata, the rank stratification in the space of matrices, except possibly at the origin, right? So then it has to be transverse to the rank stratification in a punctured neighborhood of the origin. So this is a little stronger, but it's a condition that holds in general. That means then that if you take a X in U, which is not 0, and if the rank of f of X is I minus 1, then F has to be transversal to the strata Mni minus Mni minus 1 at this point. Okay? We can assume that F of 0 is 0, right? Because if not, I can reduce. Let me put this here. Quickly, right? So if you have a matrix which does not have rank 0, so some matrix that I can reduce by elementary transformations in something like this. And the way I put here, if I'm considering an m by n matrix, and this, if this is just 1, then this is m minus 1 cross n minus 1 matrix, right? And it's easy to verify that the ideal that defines the variety is the same for F or for F prime, okay? Okay? So, any question? Okay. So, let's look at some consequences. Okay. Let me look at some consequence of the transversality assumption. So now I have an EIDS. So defined by an F, which is transverse to the rank stratification away from 0. So it's clear that the codimension of X is the expected one. It's clear that the singular set of X, which is F inverse of MNT, is, if it does not reduce to 0, it is another EIDS. It's clear that it's Cohen-Macaulay. Let me leave this for a little bit. So do you agree that these conditions come easily from the definition of EIDS? So EIDS is transverse to the rank stratification away from 0. If you take a sufficiently small representative of the germ, the transversality condition holds for all points different from 0. Well, then if you have a generic point that's transversal, you already have this. You already have the expected codimension. And this, using the Egon-Hochter result I stated there, gives that X is Cohen-Macaulay. So our determinantal singularities, defined in the way we did, are always Cohen-Macaulay. Okay? And this also comes directly from the transversality. But just to remark that it's possible that this reduced to 0. Okay? And also it follows that X has an isolated singularity at the origin, if and only if n is less than or equal to m minus t plus 2, n minus t plus 2. Right? Why? So what is the condition for X to have an isolated singularity? That F has to avoid the singular set of the generic determinantal variety, MNT, right? And the singular set of these varieties, MNT minus 1, which has codimension m minus t plus 2 times n minus t plus 2. This is the codimension of the singular set of this variety. Then the condition so that X or avoid the singular set or meet the singular set only at the origin is that, because if n is less than this dimension, then F does not hit the set. And if it's equal, it may hit at isolated points, right? With these conditions on transversality, we get what you want. I will explain later, but when n is less than n minus t plus 2, n minus t plus 2, I call X an isolated determinantal singularity. Okay, but, we can see why exactly now. Well, before I change a little bit the subject, I will put this diagram here so that you have this diagram in mind, right? And what happens is the following. So, in fact, what we are talking are represented here. So we have the space of matrices here and my universal objects there. This equation, this G here are the T by T minors defined in the matrix here. So they define, G defines MNT, right? And F is the representation matrix. And of course, the composition, F, right, is the coordinates of this composition here are F1, F2, FL here, whose ideal generated by F1, F2, FL defines my X as the variety of this ideal with coordinates F1, F2, FL. And from the viewpoint we want to stress, we just look at X equals F inverse of this. Okay? Any question at this point? Any remark? Is this clear? More or less? Okay. So then we will talk a little bit now about deformations. From here until the end, it's possible that I will not be able to go until the last slide. But from here until where I can go, I will introduce some subjects that I will take again in the lecture tomorrow to give more precise definition, okay? So we want to talk about deformations of the IDS. Deformations, in particular, is smoothing. Smoothing is a deformation which is non-singular, right? In general terms. Deformations, in particular, smoothing of an EIDS of type MNT are also EIDS of the same type. They are defined by by a perturbation of the matrix, right? So a deformation Fs of F, we call a deformation a stabilization of F if this deformation is transverse to the rank stratification at all points, right? So the stabilizations of a given F exists by tone transversality theorem. And I will give an example that you can have an idea how we do to prove that these deformations exist. So given a stabilization of F, we can define the corresponding determinantal singularity given by XS, which is F inverse, Fs inverse of MNT, and that we call essential smoothing of X. This is definition given by Eberlein Guzenzalt, right? So the essential smoothing of X is the determinantal singularity defined by a stabilization of F. In general, XS is not smooth, right? And we will see along the course something about this. We can also give similar definitions, this one that we just saw, to families. So we can define similar notions for one-parameter families, for instance. We have a one-parameter family deforming F, and we can use this one-parameter family to define a family of essential smoothing. Let's look at one example. Well, before I comment, the topology of the sensory smoothing, we will see in the next lecture. The topology of the sensory smoothing is uniquely given for a choice of M, N, and T. And we can call this essential smoothing, which is uniquely given, a singular Milnor fiber of the EIDS. So we'll discuss this next lecture. And I will give one example. So for generic values of A, B, and C, I'm looking at this family. It's a 3-parameter family of matrices. When the parameters are 0, A, B, and C are 0, I get exactly the triple point. Right? When ABC is 0, we get the corresponding determinantal singularity is the determinantal curve, which is the triple point. Here we have, so now I'm representing the same triple point, but using the representation as, so we have 3 irreducible lines meeting at point, but it's complex line. So as real varieties is just 3 copies of R2, right? 2 copies of surface. And if I take A, B, and C generic parameters in my matrices, we get a smoothing of X, which has more or less this topology. And we can, in the next classes, see that the topology is this one. Okay. I just want to remark that to use the transversality theorem, right? You can take this F tilde here from C3 cross C3, taking values in the space of matrices, and you can see that the big F, depending on the variables and the parameters, is transverse. It's easily to see that it's transverse because it's the differential is surjective, right? And then we know by Thom's elementary transversality lemma that for almost all values of the parameters, the map is still transverse, okay? So this is the proof that in this case, the essential smoothing is one smoothing. And I will leave this part of Cohen-Macaulay codimension 2 for next class, right? I start with this. And that's it. Thank you. These are some of the references that had been important for this lecture. I mean, we will keep the reference according to the lecture to don't make a long list. Any question? Remark? Please? Yes, Juanjo?
Okay, so I'm sorry I arrived a little bit late. I don't know if you mentioned it at the beginning, but the case of complete intersection, I think it's important to remark that complete intersection is a particular case of determinantal singularity. So when you take a matrix which has only one row or one column, then the associated determinantal variety is a complete intersection.
Yes. In fact,
and the condition of essentially isolated determinantal singularity is a generalization of ICs, of isolated complete intersection singularity. So I think this is important to mention.
Yeah, maybe it's good to stress what you said. I mean, I think more or less I say this because I went back to the case of ICs and point that we want to extend to a class. But in fact, we have the hypersurface, and then we have a bigger class, which is the class of ICs, and we have a still even bigger class, which is the determinantal singularities. And as Juanjo said, any ICs can be represented by a 1 cross P matrix, right? A matrix with 1 line and P columns. Thank you, Juan.
Well, another thing is that in the case of ISIS, you have the action of the contact group K, and we saw last week that we have a bijection between the isomorphism classes of ISIS and the equivalent classes of the action of the contact group. For the case of determinantal varieties, you can also define an adapted version of the contact group, which is called the KM group. And again, you can see that the isomorphism classes of determinantal varieties, you have a bijection with the KM classes of this group. And then you can use again the infinitesimal methods. You can define the T1 and the versal deformations, the transversal deformation, and more or less you can generalize almost everything of the ISIS case.
Yeah, this will be the subject of next class, not next lecture. Yeah, so next lecture will be singularity theory of matrices, right? And we do exactly the parallel what we did in the ISIS course for the determinantal singularities, but with the necessary changes, of course. Okay. Okay.
One more remark, maybe?
Yes, sure.
Or did somebody else want to go first? Sorry. On one of the last slides, you say that the determinantal Milnor fiber is well defined for a choice of M, N, and T. But I think there's a subtlety there. It might still be possible to find two matrices of the same size with the same size of minors, which have different smoothings. Nobody knows. So as an exercise to the students, you saw Pinkham's example, and it was clear the matrices had different sizes. One was 2x4, the other one was 3x3. But it might still be the case that you find two matrices of size 6x7 and the 3 minors and get different smoothings. That's if you find that, I think that would be nice. If you let the community know.
But what we'll do in next lecture will be studied in singularity theory of matrices, and we will study unfoldings, and we construct the unfolding of determinantal singularity. And using the unfolding, we know that in the complement of the bifurcation set of the unfolding, we have only one topological type. And this is what I mean when I say that we have a unique type. And depending on the dimensions, we can say even a unique analytic type. But depending on the dimensions, I can only say that we have a unique topological type at least, right? Okay. Well,
Say a short question. I wonder, so if ICs generalize hypersurfaces and determinantal singularities generalize ICs, is there something more general than determinantal singularities that?
well,
Yeah.
Oh, yes. I mean, there are other classes of singularities, right? So there are even isolated singularities that are not Cohen-Macaulay, for instance, right? And that they have a very complicated algebraic structure, even if they are easy geometrically. For instance, if you take a map from C2 to C4, right? Generically, it has isolated singularity. And, but this is not normal, right? Exactly because it's not Cohen-Macaulay, right? Because it has isolated singularity. Okay? Well, I think we are over time now, right? We can discuss more later. Thank you. I think we can have 5 minutes break before starting the next lecture.
the blackboard.
Okay.
And sometimes in intermediate time, I will spend.
I will follow you whatever
Yeah.
you do.
I watch certain things at home, and so.
Okay, thank you.
Yeah.
Good morning, everyone. As you may know, I am the technician here. I'm supporting all the events that's held in here in ICMC. And I have a question, pedido. I have to ask you just when you going to make any questions after or during the presentations here, please raise your hand and wait until the microphone comes to you. Because we are recording and we need to register your questions, okay? Thank you and have a nice event.
So we are not online yet, and I have nothing on this screen except the. Okay, so seems that we are at the air. Okay, I will continue my lectures about non-isolated singularities, and today I will talk about polar degree. But before doing it, I will show you the website of the school. Since an enormous amount of work has been done on the website, even during the weekend, by different people, even with some misunderstandings, but now many things are there. Not only the timetable, but you can also see the courses and material about the courses. And so, and if you click on most of them, they give you the right link. It's not always the case. If you want to see special things about our course, Mihai and Mies, you have to go to this line. But especially if you go to the thing introduction, it should work, then you get some extra information we have put there, so that you have direct links to our material, but also direct links to the material of the years before. So this can become much easier if you want to see Mihai's lecture. You have to click here, and you find the material I explained in the name of Mihai. Okay, let's go back now to today's talk. Just have to take the right file. That will be this file, and I have to go back to the beginning. Okay, so this I can take the mouse and take now the full screen. Okay, in certain sense, I start independent of what I have been done last week. But I will need several ingredients of last week if I go on. So it's not really independent. Okay, so we take now a complex projective variety of degree D. So just as in Laurentio's lecture. And at this moment, the singular set is arbitrary. So we have a polynomial of degree D. And we define a concept which is called topological degree of the gradient. So what is this map? It's connected with the function f, and you can write down the gradient df dx 0, df dxn up to df dxn. And what you do, you take its projective image. So for each point, So this is phi, this is the singularity. For each point, which is not a singularity of phi, you find a point in the projective space. So this concept is already long known and studied by algebraic geometers. One of them is a Brazilian called Simis, who works in Recife. It has been conjectured by Dolkachev that this polar degree only depends on the reduced structure of V. So, and not on the defining function. So it's something topological. And that statement has been proven by Dimka and Papadima in the following case. And I will show that case. But first I give you several equivalent definitions of this polar degree. So this polar degree is a kind of number. Okay, I take a linear, now I take a linear function, which is general. And then what I want, it's stratified transversal to the space V. So it's, in this case, not going through the origin and not being tangent and that kind of things. It should be general. And then the first step is that the number of points of the inverse images of this L is just the polar degree. Then there is something which is defined as polar locus, what I did already. So as soon as you have a map from, local map from Cn to C, and you take a linear function, you have a map F and the second vector L, then the polar is the singular set of FL taken out F inverse 0. So we had this kind of pictures for the singular set, and downstairs we had this kind of pictures to remember. Okay, so why is this the case? This polar set, as you see here, just let's have it here, is a union of lines. Why is a union of lines? Since the thing is homogeneous, so everything has to be, goes by straight lines to the origin. So to say in Cn plus 1. So this is the polar set in Cn plus 1. And the number of lines is exactly the number of this polar number. And you also get the same thing. Okay, let's make this picture. I will need that anyhow later. Origin, Cn plus 1. Then okay, this is then, okay, this is the hyperplane. L is equal to 1. And you have this, all the straight lines, and these polar curves. So this is F is equal to 0 intersected X is equal to 1. And this is a Cn plus 1. This is to say an affine part. So this is contained in Pn. This is Cn as an affine part contained in Pn. Okay, so this number of red points, so to say, is equal to the polar degree. And I have the picture also here, so it was not necessary to draw it on the blackboard. And as one remark is that you can look to this at any level, since the homogeneous structure moves L is equal to C to L is equal to 1 by multiplication. Okay, we have also to remember this picture already, which comes on the next slide. What you see is that I have here, so to say, the vertical, this plane here in the vertical direction. Okay, and then the next step is to show that the polar degree is equal to the rank of the complex link of this F is 0. So go back and what is the complex link of F is 0? F is 0 is the cone over this figure, and the complex link is that you have to take a generic plane, the linear function, for small c, and intersect that with v. So this is the complex link locally, not globally. But this complex link is the same thing as I've shown here on the level L is equal to 1, but only in a neighborhood. But since this is homogeneous, then the total picture will be no different from the local picture. Okay, now continuing. Okay, then, so we want to show that that is the rank of this homology group. So we go back to the previous page. So what I have here is the complex link. Then there were some critical points which are not on the complex links. These are critical points of the function f restricted to this hyperplane. Okay, so they are here. They have not a value 0, they have other critical values. And as I explained last week, you can always do the construction starting with this double 8, so to say, and then adding cells for each critical point you see. After doing that, your space becomes contractible. I just repeat, but it's always good to repeat. And that means that if it's a space becomes contractible by adding cells only in one dimension, then it must be a bouquet of spheres. And the number of spheres is equal to the number of points. Okay, we know now what our complex link is a bouquet of spheres, and the amount of spheres is equal to the polar number. And that's, I think, written in the text over here. Matthias.
One question. Yes, so we are using, in the affine setting, we are using the function f
Yes?
as a Morse function on, or relative Morse function, starting from f equals 0 and then filling up the space?
Yes, more or less. It works already if the function f has isolated critical points outside, but if we do it generic, all these points will be Morse.
Okay, and I'm wondering, how do we deal with what happens at infinity? Why
Since this is transversal at infinity, nothing will happen at infinity. And anyhow, for this complex link statement, I have not to go to infinity for my values of t.
I see.
That's some other story which comes later in much more detail.
Good, thanks.
Okay, and then the last step is that that we have this local picture, which is showed over here, which is equal to the global picture. And then, so the result that we get now otherwise it's not continuing, is that we have showed this statement that the homology of v minus h, since the big picture is just phi minus h. The hyperplane at infinity is h. And that the polar degree is equal to the rank of this affine space. And that was, I proved this for adding cells for the local thing, but outside this neighborhood, nothing is going to change, and you find it over the. So from now on, you can forget the algebraic part and the algebraic definition of polar degree. So it's just a topological thing, or it's the n-1 homology of the affine part. And for generic plane hyperplanes, this affine part is a bouquet of spheres. It will not be true for non-generic planes. Okay, this was this. Okay. Were there any questions? Okay, then the point was, can you give a formula if you have isolated singularities only? So if you have a picture like this, the usual picture, or not, take some other picture. If this is phi, homogeneous of degree d hypersurface, can you tell what the polar degree is? And this was the formula from Dimka and Papadima. And the answer is this number. So there's a fixed number for a given degree, this fixed number, and then you had to subtract the number of singularities, the sum of the Milnor numbers. In this example, I have 3. And okay, this if there are no singularities, if you have the smooth hypersurface of degree d, then the answer seems, according to this formula, to be d-1 to the power n. But anyhow, we will not prove that in this way, since we will use that we know that in the smooth case, you get this answer. Okay, I copied something of my handwritten notes. It starts again with repeating the theorem. And here you see my curve. And I have to take out this hyperplane. And then we use more or less the thing we are going to do is to compare the singular guy with a nearby smooth guy. Just that was done by Laurencio already in his lecture. And then although it's not pictured here, you will see that away from the critical points, the pictures will be equal. And near to the critical point, the difference is that you replace a piece of Milnor fiber by a point. So the difference between the Euler characteristic of the smooth guy and this guy is just the sum of the Milnor numbers. Let's look if this is written here. So this polar degree, or difference of polar degree of both, is difference of the Euler characteristics, since they were just the Betty numbers with the right sign. And then if you compare these, if you want to compute these, what you can do is to say, okay, the Euler characteristic of the affine part is the Euler characteristic of the projective part minus the Euler characteristic of the intersection. So I explained more or less, if you compare the projective parts, that the difference is the sum of the Milnor numbers. But if you take this generic transversal intersection over here, you will see that there the contributions are equal, they don't differ for phi and for phi epsilon. Okay, now I have all the ingredients. The only thing I have to know is that the Euler characteristic of this guy, of the generic smooth hypersurfaces, is d-1 to the power n. And did I prove that already, or do I prove this on this? It is not proved here, but in fact, the generic hypersurface of degree n is given by this equation. And if I take the affine version of this will become a generic function of degree d, and its Milnor number is d minus 1 to the power n. And that's what I need. Okay, so now going back, dim kappa dima makes it possible to compute the polar degree for if I have isolated singularities. And today the talk will go about isolated singularities only from now on. Tomorrow I will say again a little bit more about non-isolated singularities. Okay. Then there is a special class where the polar degree is equal to 1. They are called homoloidal or homoloidal. I'm not sure how to pronounce it. And why people think they are important? Algebraic geometers, they like birational mappings. And in this case, this gradient map has degree 1. So it's birational. And then just algebraic geometry is very happy. Other polar degrees could be interesting. Then the polar degree is 2. You have a kind of double cover. But nothing is more nice than polar degree equal to 1. And some other interesting case I will talk tomorrow about that is polar degree equal to 0, which has a very independent interest. Okay. Now, if you look to the formula we had before, then the only smooth thing where the answer is 1 is if d is equal to 2. And all the others, hypersurfaces, they have some other thing, some higher. Okay, now we go to use a theory of Jun Hu. And Jun Hu is, just let's try to go back to this for a moment in order to show you Jun Hu. This is Jun Hu. And I show him because he is the winner of the Fields Medal of this year. And he was not especially studying singularities and Milnor numbers. He was interested in things which are on a much higher level. But on his way to the theorems he wanted to prove, he needed just the concept of Milnor number. And there is a very good interview with him. Mihai also talked about that in his introduction speech. And the introduction speech and the information about the talk you can reread if you go back to this introduction page via the website of the Institute. And okay, so, but since Mihai and me wanted to study more about his work on singularities, and we tried to prove a small conjecture of him, and we were able to do so. And I will report about that. Okay, then we have had this. Then I have to go back to the page I had before. It's below. It's here, and I take the full page again. Okay, one of the points was that he wanted to list all the singularities with. First, he wanted to prove Dolgachev's conjecture, which I will explain later. And for there, you want to have bounds on the polar degree. And who showed this lemma that the polar degree is always greater or equal than the Milnor number of a phi intersected with a hyperplane. So if you look back to the blackboard here, here you have a hyperplane H which goes through a singularity. And that singularity Oh, it's now a point type of singularity, but also that can have a Milnor number. And that Milnor number is an underbound for the polar degree. So if you get there Milnor number 3, then your polar degree is always greater or equal than 3. So you know if you want to have polar degree equal to 1, that the singularity of the intersection is only allowed to be 0 or 1, this Milnor number. In fact, if it's singular, it will never be 0. Okay, so the proof of Hu in his paper used very difficult statements about slicing. And they all go back to papers of Mihai Tibar. We wrote some perfect statements about slicing in very general context, and that's what he needed. And the main result of that was that he had this inequality. But Mihai and me, we started to use a slightly other approach. And we say, okay, we are going to use polynomial functions, which I explain later, and we split the polar degree in 2 contributions, in alpha and beta, which are both non-negative, and the alpha will be related to this number over here. Okay. Now, going back to the formula, so each term will be defined as a Ley-Milnor number of the stratified singularity. I will show that soon. And the concepts in the proof, the general proof, are admissible hyperplanes. So hyperplanes which are stratified transversal to V. And the second thing, that the corresponding polar set is a curve. And this is a rather strong condition. Everybody say, take H generic, and your polar curve, your polar set is curve. But we want not to take H generic, since we want to take our H through a point, to fix the point. So it's no longer generic. So you have to prove a new polar curve theorem, and that's what Mihai and me did. We proved the constraint polar curve theorem. And this is what I said is written here. And in the isolated singularity case, the numbers alpha ph are just the Milnor numbers of mu p v intersected h. So the proof of alpha plus beta is pol is made in big generality in a paper. I will present the ideas in case that phi has only isolated singularities, and then you don't need the full big machine. And I will give the proof for isolated singularities now on the blackboard. So it was too time consuming to write that in detail in the PowerPoint. Okay. Pol phi is alpha plus beta. In the isolated case, isol case, so we take a singular point of phi, and we want to have the conditions, the admissible conditions are phi intersected h is an isolated singularity, has only isolated singularities. In this case, we assume p only, but it's not necessary, there could be more. The polar of, how do we write this? Always of f with direction L is a curve. This is, and h is transversal to phi outside P. So this stratified transversality is easy here. So these are the conditions. And then we know how to go to use polynomial methods. Polynomial methods. So we have this generic we take the hyperplane which we got from that constrained polar curve theorem. So, and we put this hyperplane x0 is equal to 0. So this is the constrained generic. And we put, and then we take the affine chart x1 is x0 is equal to 1, the affine chart. And then you can look to the following picture. Okay. So this is in a certain sense infinity. Here's the point P, which is infinity. So P is not in the affine part. Then I have here certain singularities. And downstairs, I have this. And I take now the polynomial P is f1 x1 to xn. So I have now a polynomial. And up to now, I've only defined the 0z, but now I can use also the other fibers of the polynomial. And the other fibers, there could be singularities. Even there could be the concept of a singularity at infinity in some isolated sense. And then we have the method of Mihai and myself in the Duke paper, which tells that anyhow the singularities of the generic things are bouquet of spheres, but they also tell you that if I take a neighborhood here and I add the other cells, this more or less the same trick as before. So then I take the inverse image of this guy, call this D0, and I can show in the usual way that P inverse of D0 with adding certain cells, n cells, is homotopy equivalent to the full space, so it's again contractible. Okay, this means that this image is equivalent to a bouquet of spheres, n-1 spheres, and this number, the number of those spheres, the number is defined as beta VH. So that is the number of beta, which is in the formula. Okay, so this was beta. So then there is a small complication, not that I really wanted not the tube over here, but I wanted this fiber. Oh, that looks no problem. You squeeze the tube to the fiber. And but that's a mistake. You can try doing that, but you cannot do this at infinity. In fact, as you see in the Broughton example, the homology of the tube will be different from the homology of the fiber. But the Euler characteristic of the tube, you can show is equal to the Euler characteristic of the affine fiber, phi. So that's the good thing. And since we have only to do with Betty number, then it's the right thing. Yes.
Can you say more about why the topology of the tube, the homotopy type of the tube, is different from the fiber?
You take Broughton example, and you see the difference. Anyhow, you cannot, since P was a singular point here, you cannot longer have your vector fields in the right way. You can contract them, but there will be some kind of cell attaching. So it's no longer trivial at infinity there. That's the point. And it's a good exercise to compute this in Broughton's example. Okay, so am I almost ready with this? Okay, then we do it the other way around. Okay, let's go back to this. Okay, what about alpha? So in fact, for the polar degree, I have to compare this with the generic chi. So what I have to do is to first to write as corollary that the Euler characteristic of V minus H is equal to plus beta VH is equal to the polar degree. That's what. So I want now to understand this, and for that reason I'm going to compare it with pi minus H G minus the Euler characteristic of V minus H. So this will be the generic hyperplane, and the generic hyperplane is related. This guy is 1 minus 1 to the right power times the polar degree of V. Okay, so where is this generic hyperplane if I look here? So from this non-generic hyperplane, I can make a generic hyperplane by moving over here. And then it's better to show that I had a kind of singularity here. And a better picture is perhaps that I had this picture. So this was my H. And then I move this to H epsilon. And then you see that I have exactly the construction of the local of the local link. So the difference here, the difference between those two things is related to the sum of the Milnor numbers of X intersected H, of this complex links numbers. So that is, in fact, what you do is you first consider again, as I did before, the same thing for V minus H minus the Euler characteristics of V minus Hg, so the closure. And then you find the difference is up to sine sum of alpha p Vh, which is the sum of these local Milnor numbers. And then, okay, now I have concentrated the difference. Okay, and so then I have here the number polar degree. Here I have also Euler characteristics. So I have to replace this Betti number B also by 1 plus minus n to the minus 1 to the power n times beta. And if you do that, you find that pol V is sum of mu p V intersected H plus the number beta VH. And since I took only 1 point, you find that in our case, pol v is greater or equal than the mu p of the single point of the hyperplane section. It took longer than I thought, but this was the ingredient of that Mihai and me had. So we changed the slicing method, so to say, to the. No, it has to come back, and it will come back in some time. We have to change the slicing method to the proof of this inequality. Okay, going back. So this we have shown this inequality now. Okay, now we will go to this statement. The classification of hypersurfaces with isolated singularity of polar degree 1 and 2. And 1 is proved by who, and 2 is proved by us. But let's first look to the statement. Statement is that polar degree 1 only happens in case of homaloidal singularities in 3 cases. This case we have seen already, and you can even check, since if you differentiate then you see you get something of degree 1. Then you have the 3 concurrent, the 3 lines, non-concurrent lines, and you have here already a smooth conic and its tangent. Okay, so this is the Dolgachev's list, which was proved for curves and surfaces, but not in general, and who used his bound to do this in general. Then you have a longer list, which was a conjecture of who. And the longer list consists of several things. First, cubic surfaces, and with singularities. The singularities are written here. Here you have 2 singularities on the curve. Here you have 3. If you are, yes, they have something in common. Do you see that? Milnor numbers count up to 6 all. And these are the pictures of them. So I like pictures better than the formulas. Okay, they are made by people in Kaiserslautern or Mainz. Then you have plane curves, 9 types. So you have not to memorize them all, but you can see that the Milnor numbers count up to 7 here. So, and that follows from this Dolgachev formula that it should be the case. And the last one, they count up to 2, since they have degree 3, and then Dolgachev's formula told them that this has to be the answer. So you have a list. And here you have pictures of the curves, and the idea was that you have to show that there are no others. So it's easy to show that they have polar degree 2 or 1, in this case 2, and but to show there are no others. Okay, so this was the tool. So what we have to do is to bound the number of possibilities. So we have to find out what type of singularities are allowed. So I knew about the singularity of the hyperplane. That can be in the polar degree 1 case can only have Milnor number 1. So the 2-jet of is still sum of squares, but with 1 variable missing, and so the answer can be only the AK singularity. If you have the mu v intersect at h is 2, you can only have singularities of these classes, and you have to go to the course of last year where this was proved in detail, and you can also read this in my dissertation, since I made classifications there. And the names, they are listed there. You have also not to memorize. There's a finite list. They start always x to the power q over here. Now, the next deal is how to get this, to use this bound. So if you take this generic plane at infinity, and you can always write you f in this form, this constraint generic plane. And then I replace the x0 by s. So I now look again to the affine function, and then you see that you can homotop your function, including the singularities, to the case that s is equal to 0. And then you have a very well-known singularity, the fd, which is the generic singularity of degree d. Here is a set of lines. And the idea is that during this deformation, the invariance of these singularities, of these local singularities, they move to, let's first say the Milnor lattice, so or the Milnor fibers. They move to the big Milnor fiber of this guy, and they are more or less included in that. So let's forget about this for a moment. If I have the local Milnor fibers over here, the local Milnor lattice, they will be included in the Milnor lattice of this singularity. And besides classification of singularities, this was also the statement I proved in my dissertation on page 74 in 1974. And then the idea is that you need a kind of way to use this. And what I did was, or we did, was to use the intersection matrix of the singularity, but this is not explained. So I will do that in one moment. So I forget about this, with some other invariant, which is using the eigenvalues of monodromy. So Steenbrink and Varchenko has defined spectrum numbers. What is a spectrum number? Is something which looks very difficult. But anyhow, it's a logarithm of the eigenvalue. So the eigenvalues of monodromy we know already. And we take its logarithm, everybody learned it in school, but we give them an extra level, and this level comes from some more difficult thing, a kind of Hodge decomposition. Okay, if you know this already, it's fine. If you don't know it, you say, okay, I remember logarithm of eigenvalues with some extra structure, but if you drive a car, you also know exactly what is happening in the car. And the important thing is that this spectrum is semi-continuous on the deformations. And that these spectrum numbers are computable. So this part of the text is to not to read now, but to reread if you want to see that. And I say that already in words. Okay, then it's good to explain this principle. And I make this now a little bit bigger. So what is this principle of semi-continuity? So the principle is as follows. You take the spectrum of this top singularity, this x to the power d plus y to the power d, etc. This is easy computable, and they get dots here. Then you take the spectrum of E6, so you just compute the eigenvalues, more or less in the way I explained this to you in the session. Also there, the eigenvalues came sometimes over 2 pi, but now you don't reduce that. And the principle is that if you have this multi-adjacency, then the red dots has to be more or less, so in a nice way, in between the blue dots, of are they the other dots, the central dots. If they are not, then there is no adjacency. And this principle can also be written in an exact formula, but I think the picture will tell you that is how this works. And for the next n is 2d is 4, this is the given set, and all the examples in whose list they are here, and you see this works perfect. Okay, that we know now. This works perfect. Then I go back. Yes, and now I go. Yes, Matthias.
Yeah, sorry. For this picture, you get the spectral numbers are the dots on the
Yes, are the dots, yeah.
towards the left and the right. And why are there sometimes one horizontal line and several horizontal lines?
Yeah, some have two singularities, A1 and A5. And this is here this is the A1 eigenvalue,
Okay.
and the others are the A5. That's
I cannot see well. It's the first case, n equals 3 and d equals 3.
N is 3, and D is 3.
Oh,
Yes.
okay. Thank you.
So you can, so this is already on the web. Dus if you want to see this this evening, you can go there. Okay, so what is now the trick? So you have to study all the cases which should be the next cases in the classification. If you can show that all the next cases don't satisfy this rule, then you have ruled out all the deeper possibilities, and you have proved this. And I went to my friend Joseph Steenbrink, since he is a specialist in spectrum numbers. And after some saying hello, it is just 1 hour drive. He said, okay, Dirk, I can compute all the spectrum numbers you need, and I'm always going to learn you that. And I want to show that it is not difficult as soon as you accept the algorithm, which I'm not going to explain, but you will recognize, anyhow, the Dutch language. And second, you will recognize a kind of Newton diagram, and you can compute these spectrum numbers from the Milnor algebra, from the code generators, by giving all these points, x and y, certain weights. And in each pieces, these weights are related. So you take if this is quasi homogeneous, and then you give the right weights in this sector and in that sector. And so then you see that these numbers, you have to add them. And it's almost the same as I did on Friday afternoon in some other context, not in the Milnor algebra. Okay, so what happened at the end was that he and we could show that the list was complete. All the other things have been ruling out, and this is 4 years ago, I think. And this was the end of the proof of this conjecture. And we also proved a small second conjecture of him, but you will find that in the notes. I think my time is over. Thank you very much. Questions? No questions? So you should have your own microphone.
One question. You had this example for a generic projective hypersurface that the polar degree was one number which did not depend on the hypersurface as long as it's sufficiently general, as it varies in some Zariski open set. And I was wondering, do you know if anybody was using obstruction theory, topological obstruction theory, to prove the Dimka-Papadima result and related things?
I don't remember.
Okay.
No, I don't know.
Yeah, let's maybe discuss this. I would like to see this.
Okay, then we will start with a late break.
Fernández from the Universidade Federal do Ceará in Fortaleza, and he's going to present us the course C3 about Lipschitz geometry of singularities.
Well, thank you for the introduction, Juan, and welcome everybody. First, I'd like to thank the organizers, Mihai and Raimundo, for the invitation to give this lecture. It's a great opportunity to us to talk about some basic of Lipschitz geometry. So I use the blackboard. Then let me say how this mini course is organized. We shared this in four lectures. Have one of them today, and today is divided in two parts. One for introduction, and the other one is for classification of one-dimensional real singularities. Okay. And tomorrow, we also have two parts tomorrow, but both are about tangent cones. This is definition, examples, and basic properties. Sorry. Parts. And the other part of tangent cones, the study of tangent cones under the by Lipschitz transformation. Transformation. This part here will be delivered by Edson Sampaio. And Wednesday is a free day. We don't have Lipschitz geometry course on Wednesday, and you resume Thursday with two parts. One of them for L and E singularities by Edson Sampaio. And the other one is multiplicity. I mean, is the behavior of multiplicity under by Lipschitz transformation. This is by me. And the last day is Friday. Friday, the lecture will be online by Zbigniew Zielonek. He will talk about embeddings. Embedded. I mean, existence of embeddings is Zbigniew. Zielonek. And the other part on Friday will be delivered by Lev Birbrahi. This first part is about the existence of embeddings by Lipschitz embeddings, and the other one is about some obstructions to embed sets in Rn. This topic is called metric nodes by Lev Birbrahi. This two online, remote, I don't know. Okay, so I use some time in this lecture to do an introduction to explain exactly what I mean by Lipschitz geometry of singularities. Okay. So let me say what I mean by local geometry of singularity. Okay. let me precise exactly what is this in a mathematical way. Definition. The idea is to say precise what I mean by two sets. We have two sets, X in a point belonging to X and Y, and a point belonging to I. I'd like to say I'd like to define what I mean by the following. The X looks like Y when you look close to P. Okay? If you look X close to P, I want to say what I mean by the local geometry of X near P is the same of the local geometry of Y near Q. Then X in Kn, K can be R or C, Y another Km, not needed to be the same, and P is a point of X, Q is a point of Y. I say the pair XP is diffeomorphic to YQ if there exists neighborhoods U of P in X, I mean U is that, and V a neighborhood of Q in Y, V is that one, and diffeomorphism between U and V. Okay? This is the precise definition of what I mean by the local geometry of X. What is the local geometry of X near P? Is the equivalence class of this pair when you look this equivalent relation. This is the local geometry. Then the local geometry of X is the equivalence class of X, P. So let me define what is a regular point. P is a regular point of X regular point of X if XP is diffeomorphic to K and 0. When we are diffeomorphic to a plane, a linear subspace, you say your point is a regular point. At least when X is an algebraic set in Cn algebraic, the most of the point, with pure dimension, okay? We don't have a mix of dimension. We have a cone and we have a line. This guy is not pure dimension. We have some components with one dimension and the other one with two dimension. So at least when we are pure dimension, the regular point are the most of the point of the set. And the special points, here we have a name for special points. If P is not regular, we say P is singular. Then the singular point is the special one. So how can you show that singular points exists? I'm sorry for the professional mathematicians. I've prepared these classes for undergraduate students, and how can you show that the singular point exists? I mean, example. Take x given by this equation. Let's call the cusp in R2. The picture of this set is well known. Let me use picture here. And this point here is the local, the zero locus of this function. This is x. And I'm claiming this point is a singular point of x. How can you show this? First, you see this, it's possible to identify a singular point with naked eyes, but when you try to prove this point is singular, maybe you have some obstruction to do it. Okay? Then let me introduce a mathematical object that makes it easy to prove some points are corner. This is a singular point because here we have a corner. What is a corner in the mathematical, how can you formalize a corner with mathematical language? So let me introduce this guy. This is the topic of the lecture tomorrow by Edson. This is just a flavor of this object. This object, you consider curves that enter in your set by this point here. Take curves that the initial point is the singular point. What we don't know if it's singular or not for a while. And the future of the curve is in your set. This is one example. This is another one. And you ask the initial point is equal to this guy. Then you take velocity of these curves. And you collect these velocities. Okay? Then you collect these velocities, set that gamma is of this type. Then you call this the tangent cone of x at 0. Then one of the proposition you see tomorrow is if x is regular, point of x, then this set here, the collection of this velocity is a linear subspace of the Euclidean ambient where this guy is included. X is included here. And this is K-linear. Okay. Then here we identified a corner because when you compute the tangent cone of this guy, you see this. In our example, tangent cone of x is just this half line here. You don't have for instance, velocity in this direction, because you don't have curves enter in x in this direction. We have all the curves which enter in x by this point goes in this direction with this velocity. Here we have another velocity and another one. Okay, then this guy is this half line here. 0, y. It's necessary to prove that this tangent vector is exactly that. This guy is not a linear subspace of R2. Okay.
Excuse me, you assume that gamma is analytic curve, no?
As we have to
Not
just-
only smooth, but analytic.
No, just differentiable.
Just differential.
Just differentiable. I'm asking just this guy exists. We may assume C1. C1 is enough. Okay. Any question? Please, if you have any question, you can do during the talk or even after the talk. No question. Okay. Then we will see more about this guy tomorrow. And okay, let me take another example here. This way to see the local geometry of singularity is very nice. It helps to develop a lot of mathematics along the years, but it's not an easy task to find of the list of the singularities up to diffeomorphism. In 1965, Whitney present the following example. Consider 4 lines. 3 of them are fixed. This is line y equal to 0. This is line x equal to 0. This is the line x equals to y, the xy plane. K equal to r or c. Okay. Then you start to change a bit this guy, included another line here, x, y equal to Tx, and this is a parameter. When you move this parameter, you have a family of sets which are singular in this point. This is a singularity for topological reasons. When you remove a point here, we're not homomorphic to an open subset of Rn or Cn. But if you want to see the tangent cone of this guy here is this guy itself, because this guy is homogeneous. Then this is not a linear subspace. So the example of Whitney, let me call this guy xt. The xt is not diffeomorphic to xs for t different of x generic. Actually, when you look this guy with naked eyes, they looked very similar. They look very similar. But Whitney showed that they are not the same from the at least from this differentiable viewpoint. The reason is, if you suppose you have a diffeomorphisms conjugating both guys, then when you take the derivative of this diffeomorphism, the derivative is a linear map that sends 4 line to 4 line and send the origin to the origin. Then you have a linear projective map sending 4 points to 4 points. Then there is a well-known invariant associated to these 4 lines, which is called the cross ration. The cross ration of this line should be preserved. Then they are not diffeomorphic if the cross ratio of those lines are not the same, if T is different to S and they are generic. Then there is obstruction, but what this example are saying to us is if you try to classify all the models, if you try to find a list of models which represent all the local geometries from the differential viewpoint, we don't have discrete invariants to do that. As a consequence of this example of which you have many infinite, uncountable local geometries. Then it's not possible to classify just using discrete invariants like multiplicities, Miller number, etc. Okay? Then it motivates, at least for us, to think another point of view to study the local geometry of singularities. Let me introduce now the Lipschitz local geometry. We move from this differential viewpoint to another point of view. And now I will introduce this local Lipschitz geometry, okay? It's okay for now? Okay. Let me recall what is a Lipschitz map. Consider 2 metric space, A and B metric space with respective metrics dA and dB. A map between from A to B is called Lipschitz. Lipschitz. If the distance between the image of 2 points are controlled by the distance between the points itself in the following way. The distance here in the image of 2 points, X, and any 2 points is not greater than a constant, then there exists a constant such that the distance between those guys is not greater than the distance between the pre-image of them. Okay, this is a Lipschitz mapping. We have a lot of examples of Lipschitz mapping. For instance, when you consider a differentiable map when you are looking locally, C1 map when you look locally in a ball, such a mapping should be Lipschitz when you consider the Euclidean metric because of the mean value theorem. the mean value inequality. There is an inequality. Then all the diffeomorphisms, when you look locally, are Lipschitz with the inverse also Lipschitz map. So then when F1 from B to A also exists, and is also Lipschitz, we say that F is by Lipschitz. Or I use another term here, lipomorphic, okay? Lipomorphic is a homeomorphism Lipschitz with inverse also Lipschitz. Then, during our course, most of the time, we are considered subsets of Kn with the outer metric. What is the outer metric? We have a set in Kn, and you measure the distance between the sets, take the size of the length connecting points. X and Y, and the distance outer of X and Y is the size of the segment connecting X to Y. This is the metric we are considering along the course. Sometimes we consider another metric, but when you do that, we make explicit we are considering another metric. But if not mentioned, otherwise we are with the outer metric. Then and 2 points. Now we are able to define what we mean by local Lipschitz geometry. Two sets, X, Kn, and Y, Km, and take points P belonging to X and Q belonging to Y. This is our picture. Then this pair is lipomorphic to this pair if there exists neighborhoods of P and V and Y of Q, and lipomorphism between them. Okay. Then you have neighborhood of this guy here, neighborhood of this guy here, and a lipomorphism between this neighborhood to this neighborhood. Then the local Lipschitz geometry is the equivalence class of pairs. Pairs like that. Oof. Okay, and then we can start to the course. Any question? No question.
How hard is it to see that the family of lines are Lipschitz equisingular?
There is a way using vector fields, but in the end of this lecture, we will see the proof of that. The idea here is to classify one-dimensional singularities, and the family of lines are one-dimensional singularities, and we will see that. Okay. Just some spoil of the proof. When you have branches and you collect the contact between branches, and this is enough to classify. And in case of lines, the contact between them are the same. Then, actually, this map here, 1, 2, 5, 4. This map that we intersect with a sphere of radius r, intersect the sphere of radius r, and you take this point, you send to this point, you take this one, send to this one, etc. This is a by Lipschitz map, out by Lipschitz map. When you see this along the lines, this is linear, so this is Lipschitz. When you compare two branches, in order to prove this is by Lipschitz, you have to look the contact between two branches, and the contact are the same. Then you get this map is by Lipschitz. This is exactly the proof for any one-dimensional real singularities. You will see that at the end of the. So then let's, okay, more questions? No. Okay. Then classification of one-dimensional real singularities. So before to start to classify these objects, I need to introduce some invariants. Okay, the first one, contact. I mentioned when I explained the proof of the invariance of four lines to theory. Contact. What is contact? Suppose you have two sets, x1 and x2 in Rn, both in the same ambient, such that they are path connected, closed, path connected, closed, and the zero is accumulated point of both sets in the following sense. When you remove zero from x1, you have sequence of points in x1 that convert to zero, and the same to x2. Then the idea of contact is to give a kind of speed how this guy is approximating to this guy when you go to the singular point. So you take a sphere centered in the point, let me denote this sphere by that. And you remove this ball, and you consider this the complement, and you compute the distance between those parts here. Infimum of gamma 1 minus gamma 2, such that gamma E belongs to xi, and gamma I is outside the ball. This is a function. We denote this function by x1, x2. It depends on r. Okay. The distance between those parts. We denote this function by r. When x1 and x2 are subanalytic or semi-algebraic or algebraic or analytic, you can write this function this way using Puiseux expansion. And a is different to 0. And this is the speed that we work with. Okay? Or in another way, when this guy is not necessarily subanalytic, you can compute the limit when r goes to 0 to the log of this guy and divided by log of this guy. I forgot to say, we have notes for this mini course. This note is already in the web page of the CIMPA school. And there are some exercises there, and one of them is to show that the limit exists, and this limit is exactly this guy when we are in the subanalytic setting. Okay, then this limit is the contact of x1, and let me put here contact x1 and x2. If you have two lines, it's easy to compute the contact. Example. Two lines, x1, x2, and take r here, and you measure the distance between this guy. Yeah, the distance between those lines. I think this distance is realized here. Here. The side of this triangle is r. The side of this triangle is r. Then the size is comparable to r. Then the contact, in this case, my function, when you develop your function, this function is r power 1, and something, maybe there is no something here. Then this contact is 1. So let me see other example. Example, a kind of cusp. We start the talk with cusp. No? The first singularity we present here was a cusp. Then x in R2. The picture is the picture. X2. Then what is the contact between this cusp? We have to take a sphere of r, of radius r. You remove this guy and you compute the distance between the complement. Okay? Here, the distance, I think, is realized here. For this exact example. But suppose it is not realized here. You don't know that. How can you compute? I don't know. The only way I know to compute this is supposing that this distance is realized here. Then you suppose this distance is realized here. And you change a bit a metric. You don't work with the round sphere. You take the sphere like that. You change the norm of R2. Take the norm of a vector by the maximum of the absolute values of the coordinates of x. Then the sphere comes squares. Huh? Maybe square like that. Squares, yeah. Okay, then in our case, if your point is in this set here, since this line is the tangent line of the set, the coordinate of y of the point is greater than the coordinate x. Then, when you take this norm to work with the sphere, when we are in the level of the sphere, the 2 points are given by the coordinated y equal to r. Then the other ones, this point here is r over 2, and this is negative. Yeah. Yeah. No, sorry. And this point here is r2 over 2r. When you compute the distance between them, the distance is 2 times twice r, 2k. This is our function, x1, x2 of r. Then the contact is given by that. Then we have a family of sets. Let me denote by that, which are pairwise, not by Lipschitz equivalent, if you show this contact is invariant of by Lipschitz equivalent. But different from what is in the Whitney case, this family here is not given a uncountable many guys which are not by Lipschitz equivalent. Actually, we have a theorem.
Alexandre,
Oh,
the lecture is 45 minutes. So after that, we could just stop for a 5-minute break, okay?
Break, yeah?
Yes, but you can finish the state of the theorem if you want.
Okay. Then just saying that for the Lipschitz case, we don't have examples like Whitney examples. There is a theorem by Mostovsky that says for Lipschitz geometry, there are only many infinite countable models of pairs like that, up to by Lipschitz transformation. Then you can, if you want to classify such guys, you can use discrete invariants. This is somehow what is saying in the theorem of Mostovsky. In this case, the discrete invariant is the contact. Then this is the Argo when you resume this lecture for 5 minutes. Yeah?
Yes, let's thank you.
Okay, thank you.
Questions, comment?
The reason for my initial question about the family of lines is that I was just wondering if the following map is obviously lithiomorphic. Namely, the map would be if we have if we have 4 lines where 3 of them are fixed, as t goes along, we are just tracing out, well, the fixed lines are just tracing out a plane. And then the moving line is tracing out a surface of some sort. So the map that I would say we use is we just use the identity on the 3 fixed lines and just use a rotation on the moving line. And that should trivialize the family as long as the lines don't coincide. Is that in fact a by Lipschitz map?
I think so. Yeah.
Okay.
Yeah. You build a continuous family of lithiomorphism. Yeah.
Yeah.
I did this. Take 2 of them. I didn't use this family, but I think, yeah. You may use this continuous, one parameter continuous family of lithiomorphisms.
The point I'm trying to make is that these Lipschitz maps are kind of flexible. You can just sort of slap them together sometimes.
I don't know. I don't know. You have to, Lipschitz is a bit different from the Whitney singularity. You have to compare 2 stratas of the same dimension. When you are looking the Whitney singularity, you have to take care with the stratum and the stratum on the boundary, which is less dimension. Yeah. In the Lipschitz case, you have to control the 2 strata of the same dimension, how they approximate each other. Is the difference. And you have some rigidity also.
Just a remark, I think in this case of 4 lines, a central point, you can use the controlled vector field to obtain the Lipschitz triviality, right?
Right.
Like Terry did to
Rotation.
discuss W regularity, right? So in this particular case,
Yeah. In this particular case, yeah. Is what Terry called is a canonical vector field. Yeah.
yes.
Yeah. You can use this canonical vector field.
Okay, any other question? So let's thank Alex again.
Thank you.
We'll have 5 minutes break.
So, may I start now? Okay, let's start. Okay, let's recall what's the definition of contact. So, the definition is right here. We have two sets. In order to make sense, in order to definition being useful, you are supposed the intersection of sets are just the singular point, okay? If you have a line of intersection, this distance here is equal to 0, and it's not useful. You have an infinite contact. So then, as we said before, you take a ball of radius r, and you remove what is inside of the ball, and you compute the distance between the complement of this guy, and you denote this distance by this function, which depends of the sets and the radius, and you compute this limit, log x1, x2 of r divided by log of r. Is an exercise to show this limit exists, and this limit is what we call the contact between x and 2. Okay. Let me repeat. When you are subanalytic, you can write this function this way, and you show this limit here is exactly this exponent alpha. Okay, then we propose now to prove that such a number is a by Lipschitz invariant proposition. By Lipschitz invariance of contact. Suppose you have X subset of Rn, Y subset of Rm. Suppose the origin is a singular point. They are closed, and path connected. Let me call this, I'm looking such sets just as a germ. What I mean by germ? I'm interested to know what happens only when you are close to the singular points. You forget about if your set is like that and close to 0, it is just this line, you forget what is far away from the 0 point, and you think your set is just that. I'm seeing this guy as a germ, okay? Goes to 0. Then if 8 from X to I is a lithiomorphism, sending 0 to 0, then the contact between x1 and x2 is equal to the contact between the image of x1, image of x2 for any x1, x2 in Rn, such that the intersection is equal to 0, closed, path connected. And 0 belonging to the 0 is an accumulation point of xy. In x, thank you. Thanks. Thank you. Yeah. You have your set here, x, and take two guys, x1, x2, take y here. We have a lipomorphism between x and y, sending the singular point to the singular point. Then what I'm saying that the contact between those branches is equal to the contact between the image branches. If this guy approximates each other with velocity alpha, then the image should approximate each other with velocity alpha. So, proof. Let's compute this contact here. Then you take a ball with radius r and take 2 points that realize the distance. Then the distance between the complement of the image branch is realized by 2 points. x1, x2, okay? They are closed, sets. Then you have 2 points in the image that realize this distance. Then, using this guy is a lipomorphism, we have this guy is greater than or equal to 1 over c. This is the Lipschitz constant. Of the distance between x1 and x2. We have x1 and x2 here. That the image of x1 is this guy, the image of x2 is the other guy. And you have a way to compare this size with this size. Just by definition of Lipschitz mapping. Lipschitz mapping. Then, I know how to estimate the corresponding sphere that x1 and x2 are outside. If this guy is r, then let me call this guy is equal to u. Then, using that my map is by Lipschitz map, the image of 8 minus the image of 0, this is less than equal to the x minus 0, and is greater than the 1 over c. This is what I'm assuming. Then, if this guy is r, we are supposing this guy is greater than r. Sorry. Then we are assuming 8 of x1, the distance to the origin is greater than r. Then the distance to x1 to r, to 0, is greater than 1 over c r. The same.
I think there is a C missing in the first line, no?
C also, thank you. C, yeah. Yeah, thank you. Then this is, since this guy is outside a sphere of radius 1/c times r, then this distance is greater than 1/c, x1, x2, 1/c. Okay? And you have this inequality, then take logarithm here. When you take logarithm, then logarithm is an increasing map. I have log of x1, x2 greater than or equal to log 1/c plus log x1, x2, 1/c. So then you have to divide it by log r. When you divide by log r is negative because r is close to 0. Then log r. Okay? In order to have the same parameter here, you change a bit this guy and put here minus log 1/c. Then when you take limit, the limit of this guy is contact between x1, x2, and the limit of that, this goes to 0, and this goes to this over that. Okay? Sorry, this is this one. Oh, 8. I'm sorry. Ah. Then when you take r going to 0, this goes to 0, and then it goes to the contact between x1 and x2. Then you prove this inequality, and the other one is similar. Take the inverse map of H. Then this contact is by Lipschitz invariant. So up so far, we have proved that this guy has a singularity at 0 is not by lipomorphic to this guy, for instance. When you see as a singularity at 0, because the contact here is 3/2, and the contact here 5/2. Any question? No question? Ricardo asked me the following question: why you do not take, in order to compute the sequence, why you do not take sequence in a branch here, sequence in another branch, converge to the singular point such that they have the same distance to the origin, and compute how they approximate each other? Why do not do that? We didn't that for technical reasons. Actually, when you try to prove you try to compute some contact, you use this, exactly that. And this is the next proposition. Next proposition is what we call the next proposition is what we call the comparison order lemma. order lemma. It was proved by me and Birbrai in a paper in 2000. Is you can compute this contact when we are in a subanalytic set, just take intersection with the spheres. Then suppose x1, x2 are in Rn, close, paths connected, and set that the intersection is just the singular point. Then, if x1 and x2 are subanalytic, if you don't know what is a subanalytic, we just need the following. We need two things about subanalytic set. One of them is if you are in the closure of a subanalytic set, this guy in this closure, you can approximate this guy using sequence by definition. Then here you can use an analytic function. This is one. This is called the curve selection lemma. And the other things, when you take functions, such that the graph of the function is subanalytic, then these functions are piecewise monotonic. We do not have function like that. When you approximate to 0, you have to be monotonic like that. We need just that, okay? What is the definition of subanalytic? As analytic sets. To have an analytic set, you have to define the set using analytic equations. When you use analytic inequality, you have semi-analytic set. When you take projection of the sets by proper maps, you arrive in subanalytic sets. And you got a lot of nice properties of it. But this is not the point of the course. So we are in the setting. In this case, you can compute contact between x1 and x2, just compute the order of this function. We take the intersection of x1 with the sphere, of intersection of x2 with the sphere, and compute the distance between them. We have x1, we have x2, we have the sphere, then this is the so-called link of x1. This is the link of x2, and you compute the distance between them. Then this function is not necessarily equal to this function, but this contact of this guy is the same of the order of this function. This function here, you can develop, since those guys are subanalytic, you can develop in this way. This is what I mean by order R of this distance. This is exponent, and the lemma say the contact is exactly this exponent when you take the distance between those links. In other words, we are saying that the asymptotic behavior of this function is the same of the asymptotic behavior of this function, even if they are not equal. We have examples where they are not equal. An example like that, x1 and x2, in this way. This distance is realized here. It's not between the distance between the links. So Let me give an idea how to prove this. Oh, wow. How to prove this. So, we have 5 minutes, 10, 10, 5, 10. 10 minutes, okay. So, let me prove this guy. We are interested to study the asymptotic behavior of functions. Then we need notation. Take two functions close to 0, and we say f is smaller than g if f is actually not greater than c times g for some c greater than 0. Oh, no negative. Okay, I use this notation. And you say f has the same behavior, the same asymptotic behavior as g if f is smaller than g and g is smaller than f. Okay, we want to show that this function has this same asymptotic behavior of this function. This is our claim. Okay. So another. Actually, this is a property. It's called isosceles property. Now take three functions like that, such that for any parameter, f of r, g of r, and h of r defines that a triangle. Suppose for any r, any parameter, we have a triangle. I mean, this size is smaller than this plus this. This size is smaller than this plus this. And this size is smaller than this plus this. Then the two biggest size should be equal in this sense. Then the two biggest size must be equivalent in this sense here. Oh. Proof is quite easy. Just a remark. Let me call the size A, the size B, the size C. Let me suppose they are the biggest one. Then A is smaller than B, is smaller than C. Then you have to show the conclusion as B is the same of C. We already have B is smaller than C. Then the claim is C is smaller than B, yeah? Then what we have is C, since this is a triangle, is by triangle inequality, is not greater than A plus C, but by hypothesis, A is smaller than B. This is 2B. 2B is the same of B according to this definition. Then we have this property, isosceles property. So we are ready to prove this guy here. Actually, I assume this guy and I will prove another one. Okay? Let me assume it. I don't have time. Let me assume. Let me assume then. Let's finish. So, proposition. I have two, x1, x2 subanalytic. And F, a map from the union of them to RP, and as a map germ. Map germ at 0. And if F restricted to x1 and F restricted to f2 are Lipschitz, and when you compute the distance between x1 of R, x2 of R, this is smaller than the distance between x1 R, x2 R. Whenever x1, xy R belongs to the intersection of xy with the sphere, then your map is defining the union of two branches. And you suppose that when you take a restriction of f to x1, this is Lipschitz. When you take the restriction of ff to x2, this is Lipschitz. Then you are assumed that when you take the intersection of those branches with a sphere of radius r, and you can control this distance, the image of these guys. The image of these guys points here and points here by the distance between the pre-image in this way. Then the map F must be Lipschitz. Then F is Lipschitz. So before proving this guy, let me show how this proposition gives us a complete classification of curves. Complete classification of curves. Then we have two one-dimensional real singularities at 0. I mean, this guy are subanalytic of dimension 1. Subanalytic. Then the picture, the topological picture of X is like that, and Y the same. Suppose when you remove the singular point, we have the same number of components. When you remove, we have one component, 2, K. Have 1, to k. Then you write x in this way and y in this way. And suppose when you take pair of branches here, x1, xy, and xj, the contact between them is equal to the contact when you take pair of arcs here. I mean, you have a bijection between the branches, which preserves contact. Assume that. Then, this guy is lipomorphic to this guy. This is the assumption. This contact is enough to describe the lipomorphic classics when you are in dimension 1. How can you prove that? Once this guy is a subanalytic branch, this is a graph over its tangent cone. Then when you take the r distance to the origin here, you take the intersection of the sphere of radius r, and you take this map here. This is a Lipschitz map. And you go in the correspondent branch, you mark R here, and you take this guy back. Take this guy in the branch I of distance R to the origin, and go to this guy with distance R to the branch, the correspondent branch in Y. This map is Lipschitz. This map to the tangent cone is identity, and this map is Lipschitz. Then this is a Lipschitz map when you take the restriction to the each branch. So in order to prove this map is by Lipschitz, when you compare branches, you use this proposition. Then you take point in this branch and point in this branch. The image goes to the correspondent branch. So the behavior of this distance is given by the contact. This is the comparison order lemma. And the behavior of this distance is given by the contact here. It is the comparison order lemma. Once the contacts are assumed to be equal, then they have the same behavior. Then this map is by Lipschitz. So I underestimate the time. Okay, I'll stop here. Don't have time. Tomorrow I will set an exercise class, and maybe we can prove the comparison order lemma there tomorrow afternoon. So I stop here. Questions? No? No question?
So going back to the case of the n lines in space, the lines that are moving really are sent to the corresponding lines by rotation then. Because you're fixing, I mean, you've got one line here.
Yeah.
You've identified a line over here that it's going to go to. But what you're doing is you're just rotating, you're keeping you're always inside the same sphere. So that's why I'm saying it's rotation.
Yeah, you're right.
Okay.
Yeah, exactly that.
Yeah. The other thing is, I mean, this is great for the one-dimensional case. What do you do with dimension 2?
Dimension 2. This is a very silly invariant of Lipschitz geometry, this contact. This is the first one. When you are in higher dimension, this is the case when you remove the singularity, you have more than one connected component. If you are in the complex phase, for instance, it doesn't happen. Even for cusp, in complex cases, it doesn't happen. Then you have to go further. You have, and then in the classes Thursday, we will define the relative multiplicities. Even when we are not, in the case when you remove singularity, you disconnect the set can accumulate each other, and it's possible to catch this accumulation using Belief geometry. When you do a blow up, take a point, you do a blow up of the set, then this is the tangent cone, then this is your set after blow up. They are accumulated. The number of leaves, you can catch using Belief geometry, and even the contact between these leaves somehow. The contact between them is not trivial like that. You have two leaves of the set accumulated in the tangent cone. Then the number of leaves is preserved, but this is just topology in this case. And what you use is the contact between them. In higher dimension, it's important to collect the number of leaves which are accumulated. This is the multiplicity, relativity multiplicity. This is used to compute multiplicity. But you also have the contact between them. You can use this contact. Okay. It was used in Puiseux pairs for complex curves. The number of leaves is the multiplicity of complex curves, but the contact between them is the Puiseux pairs, Puiseux exponent.
So let's thanks Alex again.
Okay.